Okay, good morning everyone. So recall from last time that for a field K, so from some field K, we can obtain a group by considering all the non-zero elements. So we define K star to be the set of non-zero elements in K, so all elements other than 0. And then this set forms a group under multiplication because all elements of the field have inverses. So if we look at this, as long as they're non-zero, so if we look at the set of non-zero elements, then that forms a group under multiplication. So we define K star as the multiplicative group of non-zero elements. And then we made a definition last time. So we said that a character of a group with values in the field K is a group homomorphism from the group to the multiplicative group of non-zero elements. So a character chi of a group G with values in the field K this is nothing more than a group homomorphism from G to K star. And then we made one additional definition. So we say now that some set of characters is linearly independent if it's linearly independent as a set of functions to K. Okay, so what does that mean in symbols? Well, a set chi1 up to chi n of characters, so homomorphisms from G to K star, is said to be linearly independent if for any a1 up to an in K where 0 value is allowed with a1 chi1 plus an up to chi n equals 0 implies a1 up to an equals 0. So any linear dependence, so linearly independent in the usual sense, but we're treating these now as functions to K. So if you have any scalars a1 up to an with a1 chi1 dot 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 up to an chi n equals 0, so this is the same thing as saying, so what I mean by this is that for any G a1 chi1 G dot an chi n G, this is some sum in K, and I want this to be 0. So this equation a1 chi1 up to an chi n equals 0 means that for any G, the sum on the left hand side takes a value 0 in K. Okay, So then for any, so they're linearly independent if for any such relation we must have all the coefficients equal to 0. Okay, so it's just the usual notion of linear independence, but we're treating these as functions from G to K. Okay, so theorem. Well, the first theorem is that distinct characters are always linearly independent. So I have here a field K and a group G. Then the claim is that if chi1 up to chi_n are distinct characters, then they are linearly independent. Oh, right. So we prove this by induction. Notice that if we only have one character, then it's obviously non-zero, because by definition characters take values in the multiplicative group K star. So they take non-zero values, so therefore they must be non-zero it must be non-zero as a function from G to K. So we prove the claim by induction on n. If n equals 1, then the claim is obvious, because chi1 takes non-zero values by definition. Okay. So now suppose that we have some linear dependence relation a1 chi1 up to an chi_n equals 0. We would like to prove that the coefficients are all 0. So now if there is any coefficient which is 0, then by relabeling the coefficients, we may assume that it's the last one which is 0. So if there is any coefficient which is 0, then by just relabeling all of the coefficients and the functions, we may assume without loss of generality that it is the last one. So we may assume without loss of generality that the 0 coefficient is an. And then we have, since an is 0, a1 chi1 plus up to an minus 1 chi_n minus 1 equals 0. But by induction, this would imply that all the other coefficients, and we would be done so long as any coefficient is 0. Okay, so it suffices to rule out the case that no of the coefficients are 0. So it suffices to rule out the possibility that all the coefficients are non-zero. So it suffices to rule out the possibility that all the coefficients are non-zero. So it suffices to rule out that AI is non-zero for all I between 1 and n. Okay, so suppose that all the coefficients are non-zero. We would like to get a contradiction. Okay, so now I can go back to my equation star and I can rewrite it moving the terms involving an chi-n onto the left-hand side. And then we have, since an is assumed non-zero, that chi-n equals -1 on an. And then it's the sum of the other terms. So let's write I from 1 to n minus 1. AI chi-i. I've just rewritten star, moving the terms involving a and chi-n on the left-hand side. Okay, so what we do now is we pick some any element we want in G and fix it. So fix an arbitrary H in G. And we fix some point H in G. Now let G in G be arbitrary, be another point. Then, so we haven't used so far the fact that we have a character, the fact that we have a group homomorphism. We're going to use it now. So what do we have? Well, we have chi-n-h, chi-n-g. Well, first of all, we can write this as chi-n-h, and then I can use this equation I've just got up here. Let's call this equation 1. So now let's use equation 1 and substitute in G 1 an I1 n minus 1 ai chi ig from 1. Okay, but we can use the fact that characters give us a group homomorphisms. So we can also write chi-n-h, chi-n-g, chi-n-h. So we can also write, using the fact that chi-n is a character, chi-n-h times chi-n-g is chi-n applied to h times g, because it's a group homomorphism. So then I could substitute hg into 1 to get that this is -1 over an. Like this. This is also from 1. But with now hg substituted into the equation. And now, once again, we have that the chi-i's are characters, so this is -1 over an, sum I equals 1 n minus 1. Okay, so let's call this equation A and this equation B. So then comparing A and B, we see, right, that the right-hand side of A equals the right-hand side of B. So we've now shown from A and B that the right-hand side of A is equal to the right-hand side of B. And then I could cancel the negative 1 over AN terms and rewrite it to get, so rewriting this equation. So let's collect everything onto the one side. Maybe I should say, let's leave the negatives here. So let's cancel the ANs and then let's rewrite this. Let's put both sides onto the same side. Then we get sum AI. So we now get the right hand side and move it on to the left hand side. Let's factor out the chi ig, which is common to both terms, chi ih. So now this is just the right hand side moved over to the left, and now minus ai chi ig, which is already there, times chi n h equals 0. Okay, let's just view this equation. So by rewriting this equation, we get this, and let's now view this slightly differently. So I can write this as sum. I can just rearrange it, so reorder it to make it look better. So now I'm doing h is fixed. And since h is fixed, this is some element, some constant. And thus, well, this is a linear dependence relation on the chi-i's. So this is valid for all g, for all g and g. So, right, so it's an equation of the form lambda I chi I equals 0, because if this is true for all g, it means that lambda I times chi I equals 0 for lambda I in G, chi I, the characters, lambda I are scalars, chi I, the characters. Right, so if I have this equation being 0 for all G, then I must have, if I set lambda I to be this term here, which is now constant since h is fixed, then it's an equation of this form. This is true for all g, but well, we know from the previous theorem so So it's an equation like this. Okay, but we know from the induction that the characters should be linearly independent. Okay, but by induction, chi1 up to chi n minus 1 are linearly independent. So if you have a linear dependence like this, then all the coefficients must be equal to 0. So a linear dependence relation like this in the n minus 1 variables, characters rather, chi1 up to chi n minus 1, gives you that all the coefficients are 0. But since these coefficients are these terms here, then this must be 0. But the AIs are non-zero. So we must have this. And this is true for any h, because h is also arbitrary. So the same must hold. We must be able to do this for any h. There was no restrictions on h. So then we must have that chi I equals chi n as characters, or as functions. But this contradicts that the characters were assumed distinct. So this would mean that the last character coincides with all of the previous characters, and this contradicts that they were all different. Okay, so we've now proven that distinct characters are linearly independent. Okay, so let's do an example. Let's see how the study of characters is relevant to field theory. So take two fields, K and L. Then an injective homomorphism sigma between the fields is called an embedding. So we call any injective homomorphism between two fields an embedding. Okay, and just a quick remark, well, we've already observed that any non-zero field homomorphism is automatically injective. So so any non-zero field homomorphism is an embedding. Okay, so now if we have some embedding, then it's injective, so I'm actually going to write it with a hooked arrow. So if sigma k hooked arrow for injective into L is an embedding, well, it's injective by definition, so the kernel is 0. So the only element getting sent to 0 is 0. And therefore, sigma induces a group homomorphism on the non-zero elements. So restricting to the non-zero elements, k star in k gives us a group homomorphism. Since it's a field homomorphism restricted to the non-zero elements, gives a group homomorphism taking non-zero values, sigma from k star to L star. In other words, restricting to non-zero elements gives us a character of the multiplicative group of k with values in L. So then in particular we can apply the previous theorem to some collection of embeddings. So by the previous theorem, if sigma 1 up to sigma n is a collection of n embeddings between two fields k and L, and they are distinct, so if we have some collection of distinct embeddings, then they have to be linearly independent. Because to all of them, I can get a character by looking at the non-zero elements, and then those characters have to be linearly independent, which is the same as saying that the embeddings, which is just the exact same information as the characters, just with the additional knowledge that 0 goes to 0, which is obvious anyway. So from the linear independence of the characters, you see that the embeddings are also linearly independent. Okay. So by the previous theorem, if I have distinct embeddings from between two fields, then they have to be linearly independent. All right now, theorem. Okay, so now we prove one of the important early theorems for Galois theory. Okay, so it says that suppose we take some finite group of automorphisms of a field K, then if we let F be the fixed field of that group, then the degree of the extension of K over the fixed field is larger than the number of elements in the group. So take some finite group of automorphisms of a field K. So let G equal 1 equals sigma 1. Let's just say sigma 1 is 1. Sigma 2 up to sigma n. So take some finite subgroup of automorphisms of a field K. So let G be a finite subgroup of automorphisms of a field K, and let F be the fixed field of G. So F is a set of elements in K which are fixed by all the elements of G. Then the degree of the field extension, K over F, is at least given by the number of elements G. Okay, so just a remark before proving a theorem. We're actually going to prove next time that we have equality here, but for now we only need the inequality. So we will actually later prove that it turns out that degree of the field extension is exactly G, but we don't need to know that for today's lecture. Okay. Okay, so let's prove the theorem. So to start with, suppose that, so I'm trying to prove that the degree of the field extension, K over the fixed field of G, is greater than or equal to G. So to get a contradiction, well, let's suppose that it's less than the size of G. So then it's finite because it's less than n. So let degree of the field extension be equal to m, less than n. So what this is telling us, the degree of the field extension is the dimension of K as an F vector space. Okay, so if that's m, then I can let V1 up to Vm be a basis for K over F. So let V1 to Vm be a basis for K over F then we now consider the system of linear equations sigma 1 v1 x1 up to sigma n v1 xn and so on, but with the v1 running through v1 up to vm. Equals 0. Xn equals 0. Okay, so then I have m equations in n unknowns. So it's a system of m equations in n unknowns with m less than n. Oh, and they're all linear equations, of course. So each linear equation cuts down the dimension of solutions by at most 1. So if I call this solution set star, then since m is less than n, star has to have non-zero solutions because each equation cuts down the solution set of the n-dimensional space of the variables x1 up to xn by at most 1. And I have m equations, so the solution set has to have dimension, has to be some linear space of dimension at least 1, and in particular has to have non-zero elements. So if I have less equations of a number of variables, and they're all linear, then it definitely has a non-zero solution. So since m is less than n, the number of equations is less than the number of unknowns, then the system has a non-zero solution. So let's say that the non-zero solution is y1 up to yn in k to the n. Okay, so now pick any scalars lambda 1 up to lambda m in the fixed field f. Then by definition, all of our elements fix f, and hence lambda 1 up to lambda m. So since all the elements in G fix lambda 1 up to lambda m, by definition of f as the fixed field of G, then if I substitute my solution to the equation star back into lambda and multiply them by lambda 1 up to lambda m, so substituting this solution into the non-zero solution into the system of equations and multiplying by lambda 1 up to lambda m, I get the following. So I can multiply the first equation by lambda 1, and then since sigma 1 up to sigma n all fix lambda 1, I can move it inside to get sigma 1 lambda 1 v1 y1, so putting the solution in, up to sigma n lambda 1 v1 ym equals 0, up to, so I multiplied the first, I've put this, all I've done is I've taken the first equation in star, substituted the solution in for x, and multiplied through by lambda 1. Using that, I can put it inside the parentheses because it's part of the fixed field. And now I do the same thing, but multiplying the last equation by lambda m. Oh wait, sorry, hold on. Should be yn. Yeah, m equations and n unknowns. Sigma n lambda m v m y n equals 0. Yes. Okay. So here are my m equations. Now I've substituted the solutions y1 up to yn into them, and I have m equations. And I've multiplied each of the equations through by first lambda 1 up to lambda m. Okay, so this is what I now have. Now I can add this all together add all these equations. And I get sigma 1. So now I'm going to get equations like sigma 1, lambda 1, v1, lambda m vm y1, plus sigma n lambda 1 v1, plus lambda m vm yn equals 0. Okay, so then I get this equation here, but notice that lambda 1 up to lambda m, these were totally arbitrary elements in F. And furthermore, v1 up to vm was a basis for k over f okay, so any element w in k can be written in the form w equals lambda 1 v1, since v1 up to vm is a basis. Any element in k can be written in the form lambda 1 v1 up to lambda m vm for appropriate lambda 1 up to lambda m in F. Therefore, from this equation, I must be able to, well, if w is of this required form, I get that sigma 1 w y1 plus sigma n w yn equals 0 for all w in k. And now, well, let's view this the other way around. So let's write this as y1 sigma 1 w plus yn sigma n w equals 0. This is true for all w in k. And sigma 1 up to sigma n were all automorphisms of k. So this implies, since it's true for all w in k, sigma y1, which is an element in k, sigma 1 plus yn sigma n equals 0. So the 0 function now. Now I'm viewing 0 as a 0 function. So this means if this is just the previous equation rewritten, so k goes to 0. But this contradicts that sigma 1 up to sigma n were field automorphisms, and I know from the previous theorem that they must be linearly independent. So this contradicts the previous theorem, which when applied here tells us that sigma 1 up to sigma n are linearly independent field automorphisms k to k. Okay, so thanks for listening. We're going to talk more about this important theorem next time.